Thanks everyone for your participation in this workshop. I think this workshop has been extremely productive. We've had a lot of great content, and we're going to wrap it up here in the next 25 to 30 minutes as on time as we can be. So the final panel, this is more of just an open discussion than it is a panel. We're going to spotlight Wes and John Scott, and we're going to just kind of go over, the major takeaways from the meeting. So if you have something that you think is a major takeaway, just go ahead and put it in the Q&A, and then we'll get Wes and John to kind of comment on it, and we'll bounce back and forth and kind of try and coalesce on what we think our major takeaways were. So to start this out, I'll just put both of you on the spot. Maybe John, you can go first. What was your number one kind of biggest takeaway from the last 2 days? Ready,
Well,
set, go.
oh, go. Okay. No. I started this out with a particular concern about reliability, and that's something I could easily see that I may be wrong that that's the only concern. The concern that once we get into this what we call the phase alpha power system, high voltage transmission in the lunar environment, we're exposing ourselves to a set of failure modes with the power electronics that we haven't seen before. And so I'm concerned about coming up with ways to mitigate that. Now, what I was, the point is that the people that have to mitigate that are the people who might have ambitions to create with private capital this large lunar surface power system. I'm very pleased that we've had a panel of industry people, outfits that have an industry that have ambitions to be a power provider on the moon, a commercial power provider on the moon, and that they have been online to hear the various solutions that a lot of very smart people have brought to this forum to show that it might be to solve all the various problems and engage with having a maintainable power system. I think it's quite. I'm very, very, very pleased with the participation and attendance in this. The other aspect of this that we haven't addressed here yet, and there's an action I think it came up from Julie Pate's panel from last night. It's something I mentioned earlier. A lot of talk about how you make the power system reliable. We haven't talked much about how reliable it has to be. I think we understand that for the crewed elements, of Artemis and things like that. That's the standard that comes around with fault tolerance. And of course, we may find out may learn something, and hopefully we'll learn it before we get up there, that even that doesn't maintain adequate reliability in this radiation environment. But that's something that needs to be discussed. We haven't heard from the community of those who have ambitions to create industrial facilities, the ISRU plants. How reliable do they need their power grid to be? So that's a question that's on the table, and I'd like to see it addressed in the future.
That's a great point, John. So I think that I would echo pretty much everything that John had said here. When I think about what we've, circle back, we did broad to narrow, starting with John and reliability 101, and Blanca's perspective from EHB. So we started with that big broad thing. We came all the way down to very narrow questions too. So I was impressed at how wide of a set of people were able to come together on that. And I just want to say right now that I really appreciate the time that people spent coming to here and voicing their concerns and getting those things on the record so we can document it. That's how we make sure that we don't let these things continue to fall through the gaps. So always promise that communication channels are always open. So if there's more things that came up, ideas that you have in the shower tomorrow, whatever, let us know. Definitely keep those going. What impresses me is that it is happening now. When you look at the time scales for when a lot of our industrial and commercial partners are moving out on these things, they're making decisions and cutting metal and doing things now. And so to me, that means that the moment is now to consider how we move beyond Artemis Base Camp towards that commercial grid, and understand the implications of the decisions that we're making now on our final objectives of that scalable lunar power architecture. So that would be my takeaways. I've got a lot of specifics that I've got to distill and put together on, specific takeaways that we had from each of the sessions. But, I was also, most keenly in tune to the industry panel and hearing what their needs are in particular. And again, it was a broad set of concerns and ideas on it, but I think you were right. They also expressed a need for that load, for load requirements, and yeah, the demand signal from the broader user base. So we've got a lot of good ideas, a lot of ideas of where things could get us, could bite us. But the question that John brought up was actually the one that I identified too, is how reliable we actually need to be for these non-critical loads. And that might not be something that we answer until we have a more mature understanding of the broader technologies that are going to be using these loads. We can take a swag at what those scales are going to be based on, physics times efficiency coefficients or something like this. But there's a lot to learn in the meantime. And I think one of my main takeaways is that there's a really critical need to understand where we can leverage as best as possible all the information that we're getting from these early missions so that we can learn where it's appropriate to learn and not where we where we're learning during a critical mission, right? So a call for learning with intention at every opportunity. And that implies all sorts of things. Implies, more dedicated technology missions. It could imply more incentives to share information and gather information, disseminate information across all of these players. So those are some of my major takeaways. And I'd be happy to hear you in the Q&A or in the, you can put something in the chat, what your major takeaways, additional things that you want on the record. And yeah, help John and I pontificate a little less and then hear from you.
The time is certainly now, and you both make a great point that the follow on to this certainly needs to be, something similar where we're bringing, the ENC folks and the ISRU folks in, and we really hone in on how reliable do you want your power to be, what, and we hone in on those load falling questions that all came up. Something I wanted to poke at too, and again, feel free to put stuff in the Q&A. A theme that came up over and over again in panels and in our breakout sessions was maintainability and designing for maintainability from the start, and the ability to maintain critical loads powered while you're doing maintenance on something that broke. And I just wanted to get both of your thoughts on that, and then I see Gary has his hand raised. We'll go to you after that.
Well, it's on the maintainability question. I mean, the traditional spacecraft design was it not to be maintained at all. Like our iPhones, they're not to be maintained; they're to be replaced, right?
Yeah,
Right.
1 year.
Yeah, mine's done a little bit better than that. But again, when you get into an industrial plant, that's our ambition. No, there's going to be some maintainability. Now, the International Space Station, we've gotten into actively maintaining it. And it is designed for maintainability, and there's a lot of people involved in that program that are trying to make it more maintainable or more efficiently maintainable. So it's not something that can't. It's not like something that can't be done. And again, and it becomes more important to do and more obvious to do. You're talking about a long-term mission, and of course, the space station's been occupied since 1999. That doesn't seem like that long ago, but it is. And so that has been actively maintained by the crew, and EBR and EVA and IVA activities, replacing racks and things like that. So there's a lot of work that's gone into thinking through how to make the process of changing out a circuit board more efficient. Those same lessons can be applied to the Artemis elements, certainly, and they should be. That can be maintained for a while and then expanded to this industrial plant. I mean, I have to admit, I really enjoy the little videos from our colleague at Ames with the little device walking around there and putting things together for us. It's not nearly as simple as it looks, I know, but but again, it's a rational, it's a difficult trade because everything's so uncertain. But you think about how much it costs to maintain something, to replace something out on the moon somewhere, than it is to make it to where it's just rock hard and hardened and never has to be maintained. There's a trade-off there, and I probably don't right now have the data on either side of the option to really make that cost trade.
Well, one thing that I think is pretty important to acknowledge, that even in advance of complete knowledge of how we would address some of the reliability or maintainability questions, there are low-hanging fruit for what we can do to enable that future to ever occur. So I often think about, and when we're talking about this, the sort of moment that we're going through for on-orbit servicing and manufacturing, right? So the first satellites that went up just didn't even consider that refueling could have ever been a possibility or any kind of maintainability. And so they didn't include, really bare bones, simple stuff that could have allowed that to happen. Think like a sticker that tells orientation and a fiducial, like a grappling hook, something like that. So those are some of the things where we can not even be prescriptive about how it has to happen, but by pushing this conversation, we see that our commercial partners are moving in that direction already. And we heard from Luis and we heard from Honeybee about they're developing dust tolerant connectors that they both would like to see turn into the industry standard for it. And it's not necessarily that we have to do anything to prescribe either one of those as the solution, but we're actually thinking about how we want to make these things, so that they enable that future that we'd like to achieve. And that's kind of the main idea to me, is that we can make decisions now that can enable that future. And there's a whole lot of more detailed decisions that we have to consider as well for that future. But on maintainability, there's certainly going to be some set of those kind of things, enabling actions that we can take early on.
Yeah, it looks, I think Gary might be on the phone, so we'll um oh, he's off. Gary, do you want to pose your
Yeah,
question?
my question was this, okay? Perhaps one of the things that are a takeaway from this workshop is maybe reliability, is not a static optimization problem that we're dealing with here. And arguably, it's more of a dynamic quality of service problem that we have to look at in terms of performance, availability, and security. Uh, from that perspective, I think it provides a way of organizing and integrating an awful lot of the content that we've seen in this workshop.
Mhm. Right. Yeah, and I think that, you know, when
Oh,
faced with an extraordinarily complex situation, there's sort of two options. You can sort of throw your hands up and say that there's nothing we can do, or you can find the small elements that can start and be the nucleation site for a lot of this larger scale stuff that we're working on. And I think that's a good point that we're at right now. We're making that. It just takes one little crystal seed to grow a huge bull. So Matt, I don't know if you wanted
Yeah.
to move. There's some questions into the in the Q&A I see too. I wanted to call out Tim's.
Yeah, I wanted to get to that too,
Yeah.
because that goes to things that have, been floating in the Q&A and also percolated in the breakout sessions as
Mhm.
well. So Tim wrote, there are no wire derating specifications existing for wire in a regolith powder environment. Vacuum and pressurized cabin tables exist, but they're not applicable for proper lunar power distribution design. For proper design trains to be made, wire derating in a regolith power is critical. The reliability of power transmission lines cannot even be made without this data. This is a showstopper. Can NESC put this on a high priority and make available to industry? And this just goes to a lot of the environmental stuff that has been talked about throughout this
Yeah,
workshop.
there were a couple points in there that I really thought were warranted unpacking. So for one, yes, it is absolutely true that power cables on the lunar surface are at they're at very, very low TRL, right? We haven't done this at all. And the interaction with the environment is generally something that we don't consider at the scale where these things are relevant for the ambitions that we have. And it also gets at the information sharing aspect of this. So NESC putting it as a high priority to make some more information widely available on this, I think would be quite valuable. We see already that there are proposals for working on this. That was one of the tipping points. Astrobotics, I'm sure, got extremely ambitious, at least by my interpretation of what they've shared so far. Extremely ambitious plans for how to take this on, and I think that there's a lot that could be done to make sure that they have the information that they need to succeed, and that the rest of the community also has that kind of information.
Yeah. Excuse me. And what I'd add to that is that, I started this conversation out hooked on the fear that we don't understand really how converters and other such circuits will respond using wide band gap electronics in this radiation environment. This is just as scary.
Yep. Yeah. No, you're
I
you're
mean,
spot on with that. Yeah.
and I mean, Tim's absolutely right. And in getting these questions answered, simulations run or standards set up,
Hmm.
or just studies of how the moon dust is going to act around these wires. And again, the tipping point of this robotic speaks to that to some extent, are
Hmm.
part of what NASA has to do to de-risk the technology involved in this kind of lunar power system. So this is certainly needs to be on the list along with my little bugaboo about wide bandgap electronics.
Yeah, let's poke at that theme a little further again to put you both on the spot. And I have multiple of these for myself. You know, in addition to those two that we've already poked at, what's something else that wasn't necessarily keeping you up at night before this workshop and now will keep you up at night after this workshop?
Yeah, I'll say it's something that is always in the back of my mind, but the complexity that we're heading towards, the more complex and interconnected a system is, often the more sensitive and fragile it becomes. So that's an area where I'm still concerned, that we're intentionally moving through this in a way that, as we integrate more and more broadly, that we don't accidentally paint ourselves into a corner that's gonna really bite us down the road. Um, yeah, so that's it. The sort of the scale, especially when we get to distribution across a wide set of assets, storage, loads, etc. That gets really complex.
It does, and that's the kind of thing that our colleague from Centerpoint Energy, brought up, that they deal with all the
Hmm.
time.
Hmm.
You know, and one thing my discussions with them is that a fundamental thing about this is that a difference between what we have ambitions to do and what they are doing, they and their other companies in that business are doing, is we're dealing with different failure modes.
Hmm.
You know, in a way, they're both weather. There's
Yeah,
resiliency against
yeah.
weather, and that's in just a different kind of weather. But there's another factor that comes from the complexity of the environment, and that's just what Wes was talking about. As you get bigger, more things going on, things get more complicated, and you get more independent consequences. The
Hmm.
way I've seen it characterized, and I happen to enjoy this, about the commercial power grid, is that they've got the environmental failure modes, and then you've got stupid. People driving into towers and
Yeah.
knocking them over and all that. You can't know. So they know they can never bet against stupid, but they have to go long on it. So they have to assume all the things that can go wrong, and which is something that's not out of bed with the thinking in the aerospace industry.
Hmm.
Again, it's part of trying to avoid learning something in operations. But again, as it gets more complex, and you've got, you go all the way up to the very top level in the Artemis Accords. What those are really about
Right.
is trying to avoid the stupid aspect of working with other international partners on the moon. Make sure we don't step on each other.
Right.
That's
Right.
really what that's about.
Hmm.
And again, so maybe we have to go along on stupid there too, just out of that. But yeah,
Right.
again, the complexity aspect of it is, um, no, again, compared to this, we think the space station's simple, but we haven't figured out the space station really either, not fully. So it's we
Right.
have a lot to do.
Yeah, spot on, John. I would add, there's a phrase that I like to add too, to sort of rhymes with that, is, anyone can build a bridge that stands, but only an engineer can build a bridge that barely stands. And so, we're playing along these trades where, sometimes we make a design decision that takes us down one path, but that's not always the right trade that we're considering in making that decision. So there's two sides to that. One is that we need to be very intentional with the way that we're constructing some of these trades. You know, the one that came up in our breakout was the AC versus DC trade again. And there's a whole bunch of multifaceted ways that you can kind of slice that apart. But often it comes down to mass and efficiency. But, you know, if we have enough generation capability, efficiency might not be the right metric. And if we have enough down mass where we're doing a whole ton of stuff on the lunar surface, then maybe mass isn't as critical of a trade. And maybe it's the predictability of these systems that is as critical as some of optimizing purely over reliability. So yeah, I guess that's kind of the additional sort of nuance that I'd add to, you know, not just designing for stupid, but, you know, designing for this longer intent that we have on it. Building a bridge that barely stands for 10 years as opposed to
Wanted to prompt you all with one more question, kind of from our takeaways from the breakouts before I'll give you a chance to share final thoughts, and we'll wrap for the day. You know, kind of the overarching question that I started the meeting off with was, how do we quantify reliability and how do we verify compliance? And one of the major takeaways that came up in all three of the breakouts was the need for some entity that sets the standards and takes the leadership role. And in my breakout, someone came up with the phrase a stakeholder council. And I think it was Wes's breakout that had the quote, diversity of technology, but unified standards. And so I'm curious on both your thoughts on when do we need this? Who is this? What is it? Yeah, go.
You want to go first, John? Or I can go on this too.
Not really.
Okay.
No. I mean, what it is, you know, what we have we have FERC, Federal Energy Reliability Council. You know, there's a government body, and then there's the NERC no, it's one or the other. One is a contractor for the other, NERC and FERC, but they're all about the Reliability Council, and they set standards. And you know, with them, there's EPRI, Electric Power Research Institute. That's that's the R&D arm for the commercial power utility industry. You know, and they all do exactly what you're talking about. You know, and there's you know, like a law that authorizes the NERC, and then there's, you know, FERC and and then it comes underneath that. I don't know what law there is to authorize what we're needing for this complex set of partners on the moon. Maybe that's what the Artemis Accords is about. But yeah, there needs to be a body. It's not a development organization. No, you know, it's a industrial collaboration. And you know, and again, you look at the history of how the civil power industry developed. That's exactly what happened. You know, it was all over the place, and then it got okay.
Yeah, base is where this comes from. What we heard, this was asked in the Q&A and answered in the Q&A chat to us, so you can go back and look. I think it was, if I still have it, I think Rob from GRC, Rob Button, asked the question about wanting industry's perspective on this too. Where did it go?
Oh, I remember one.
Oh, here it is. Yeah. So both we had Astrobotic and Lockheed folks talking about this, you know, capturing the public-private partnerships and doing it through government industry consensus on this, right? So I think that's a good point, is that there's industry is, at least in the voices that we're hearing from them, they're quite interested in doing this in a way that is collaborative, which is quite nice to hear, right? We want to do this because I think there's an acknowledgement that we can't do it unless we're doing it all together. So yeah, how this works, I think it's also important to acknowledge that some of the questions don't have answers right now, and we don't develop standards in advance of the state of knowledge or state of the art. So that's an area where examining what needs to be done, where we eventually want to make standards, and where there are both knowledge and technological gaps en route to those is important too, right? That's where we can apply some, you know, through the mechanisms that NASA has to fund and retire some of this risk and build that knowledge out. I think that'll be very valuable.
Yeah, thanks to both of you. I'm gonna share a little conclusion slide here and give you both just a couple minutes if you have any final thoughts to share before we wrap for the day. The floor is yours. And yeah, thanks again to everyone.
Yeah, I love this sentiment. So if I have my last word, what I would say is, there's this idea in I think it comes from computer science. I've heard it applied to astrobiology as well, but it's the idea that there's only really three numbers: 0, 1, and infinity. So before Apollo, we were a 0 off the Earth, on the moon and beyond. Apollo was 1, and we're in the process now of trying to get to infinity. And that's going to be hard. It's going to be messy, but it will really take all of us to get there. And that's the value that I see in coming together like this. And so I want to thank everybody for participating. And yeah, your continued effort and enthusiasm is what's going to make it happen. So the idea of what was it? I say urgent curiosity, but it was impatient curiosity that we heard before. So I think we all want to maintain our urgent and impatient curiosity in getting there.
And if I get the last word, again, I'm deeply grateful to Wes and the team at APL for pulling this together. I am looking forward to them pulling versions of it together again, repeatedly, because I think that's what it'll take to develop the consensus in the community. It needs to carry this forward and enable us to enable mankind to gather up what the book of Deuteronomy calls those precious things put forth by the moon.
A fantastic note to end on. Thank you all for joining, for your participation. Thanks to the LSIC team, especially Sean Young, Julie Peck, Joseph Kozak, and Sam Andrade. Appreciate all your contributions. Couldn't have done it without you. And we'll see you all next time.